Hi everyone, thanks for attending this presentation. I'm Lu and I work in the Autonomous Robots and Control Systems Lab in UC Riverside. Today I'm going to introduce a data-driven hierarchical control structure for systems with uncertainty. This work is raised by the fact that robots increasingly venture outside of the lab. When they are interacting with the environment, they are easily be affected by the uncertainties generated by the environment, like the ground effect, the sealing effect, the gust effect, and even the interactions among agents. There has been much investigations on handling those disturbances to robots, and most of the previous work focused on extracting physical models of the disturbed robots through mathematical analysis. In the 1950s, people started to investigate the ground effect on helicopter, and those analyses are still pronounced nowadays. Authors try to use either differential equations or state space models to represent the models. However, existing theoretical dynamics are derived on some certain conditions. For example, most of the models of the ground effect is based on steady flow conditions, while practical cases show unsteady flow. So these mathematical models might be inaccurate in a varying environment. To capture these complex interactions without overly constrained by conventional modeling assumptions, researchers tend to use the data-driven methods to learn this disturbance. This group tried to use the deep learning approach to learn the ground effect or the interactions among agents in an aerial robot system. Well, like most of the neural network-based methods, they require a large amount of effort, time, and data to do pre-training. And in our work, we would embed another kind of data-driven methods, the operator-based algorithm. Here, I will give a short introduction on the one we want to use in our structure, the dynamic mode decomposition. It is a way to learn the unknown dynamics from the measurements. So we could predict the states at the next time using current states and input. The key idea of this approach is to learn a linear approximation of the original system. To extract the model, we will firstly collect the measurements of the states and the input and write them compactly into matrix form. Then we can seek the best fit solutions to calculate this operator AP from the measurements matrices. Once we got this estimated model, we can use it in this linear dynamics to do prediction. So these methods utilize the traditional control theory combined with the data to equip the robot's ability to adjust the changing environment. Now, if we go back to the problem, we will find the systems share similar properties. Firstly, they will be affected when they are working online. Secondly, a low-level pre-trained controller is already in place. So we will require our structure to run fast and simple enough to work in real time. Also, we want to make use of this low-level controller. So a data-driven hierarchical structure will be a good way to solve this problem. Now we are ready to present our work, a data-driven hierarchical control structure. Firstly, let's consider the original system, which will have a low-level controller, the original plant, and when you are given a desired reference R, you want the whole system to generate the output X that follow this reference. However, because of the disturbance generated by the environment, when we propagate the system, X might not achieve the control objective. So we will reconstruct the system as a hierarchical architecture. Firstly, the low-level controller and the original plant will be combined as a new plant. Then we will insert two new blocks here: the model identification block and the author controller block. The main idea of this whole structure is to identify the relation between the reference given to the new plant and its output. Once we extract the dynamics, the model will be utilized in this author controller. It will refine the desired reference R to this R hat with this learned model. Then the refined reference R hat will be given to the robot system to propagate it. So at each time step K, we will do the following three steps. Firstly, we will learn the relation with the dynamic mode decomposition. Then this learned dynamics will be used in the author controller to refine the reference. Then the R hat will be given to the plant to propagate the system. If we compare these two equations for modeling and control, we will find the only difference is we replace the X with the desired reference. So the intuition here is, if we get an accurate estimated model, the output X will be exactly same as the desired reference. Overall, this structure enjoys two advantages. Firstly, we only refine the reference given to the robot without rewriting the low-level controller. So it is easily to be implemented in a real robot. Secondly, at each time step K, we only need a limited number of measurements to do modeling and control. So it will provide save time and space to work in real time. That's a short overview of the structure. Well, for every data-driven methods, one might raise the question, what if the data is noisy? How much it will affect the accuracy of the prediction? Here, we derive the two bound of the relative prediction error because of the noise measurements for our structure. Now let's first recalling the dynamic mode decomposition. We want to solve this operator AP from the observations XP and omega. Using the norm of delta AP to represent the prediction error and the norm of delta XP and delta omega to illustrate the noise in the measurements. The relative prediction error can be expressed as a function of those noise. And if we further assume that noise only occurs in observed states without inputs, this relative error will be bounded by a tighter bound. Here we use a toy example to show our results. We combine the noise in the measurements when we do the modeling and the prediction. The noise is normally distributed with zero mean and sigma as its standard deviation, where the sigma is settled in the range from 0.05 to 1, and each case will be performed 10,000 times to produce the average error. From the figure we can see, when we increase the magnitude of the noise, the relative error will also increase, and this loose bound expands at a higher rate than the tighter bound. That's of the most of the theoretical analysis. To evaluate the efficiency of our structure, we do the simulation and experimentally with the corrotor. In the simulation, the planar corrotor is required to reach the desired position from the origin, and those nominal parameter values match that of the physical crazy fly robots, which we will use in the later experiment. Here, we design the kind of uncertainty for the case when some parameters are approximately estimated. For example, when we build a sensor on top of these micro-error robots, it will cause a constant uncertainty on the model of the whole system. To illustrate this type of uncertainties, We aid the disturbance in mass and inertia, and they are generated at initialization and will be constant when we propagate the system. To test the efficiency, we design low density of the disturbance at case C1 and a higher density at C2. Other than our structure, we design 3 other controllers for comparison. The typical state feedback controller, the nominal linear model predictive controller, and the model reference adaptive controller, which is a parameter adaptation rule combined with the nominal MPC. As shown in this table, where we mark the best performance as a darker color. Though the nominal MPC performs good in terms of the effort, the settling time, and won't cause overshoot, it cannot achieve the control objective. It causes a large steady-state error. And this adaptive controller can help decrease this steady-state error, but it will cause large efforts and the overshoot. As for the state feedback controller, it can work well in terms of the steady-state error in the low-density case, but when we increase the density of the disturbance, it cannot even stabilize the system. Finally, when it comes to our structure, the scheme could achieve the control objective without overshoot and cost relatively less time and less energy. So this simulation shows the efficiency of our design. We also do the evaluation experimentally with a CrazyFly robot. Here, the uncertainty is designed as the unknown robot environment interactions. Here, this macro-array robot is required to follow a straight line for 2.4 meters, and an obstacle is placed in the middle of the trajectory to generate the ground effect. The ground effect is a kind of uncertainty generated by the environment. When the robot gets close to the ground, it could lift the robot up, so drive it away from the desired height. To handle this problem, we designed 4 controllers: the PID controller, the geometric controller, and these 2 wrapped with the hierarchical structure. We repeated the work in 3 different heights and 6 different velocities, and each trial is repeated 10 times to avoid bias. In this video, we show one of the examples. Here, the red line represents our structure, and the blue one illustrates the original one. The green is for the desired height. From the video, we can see we are learning with the measurement collected under the ground effect at the beginning. Our approach could drive the robot be closer to the desired height. And that's one of the examples. All the results are plotted in these figures. Here we use a circle and star to represent the geometric and PID controller separately, and they will mark the mean of each case. The length of the line is constructed by the standard deviation, and among all the cases, the red line will represent the results of our controller, and the blue line is for the original one. So this figure shows the prediction error of our structure and the original controller in different distances and velocities. From the result, we can see our structure can drive the system to be closer to the desired height compared to the standalone controller in most of the cases. Also, it performs better at lower distance and slower speed. Another observation is, though our structure can help to improve the performance, it will still be bounded to the low-level controller's possible limitations. And that might be our future research directions. Overall, in this paper, we propose a data-driven hierarchical structure to help the robots to handle uncertainties when they are interacting with the environment in real time. It is combined by two parts, an online modeling part to learn the relation between the reference given to the robot and its output, and an outer controller which will refine the reference. Using our structure, you don't need to change the underlying controller, and it could work online to handle these uncertainties. Finally, we use the simulation and experimentally with the crazy fly to show our efficiency under different kinds of uncertainties. That's all for today's presentation, and thanks for listening. If you got any questions, I'm willing to help.